Hey, welcome to The Explainer. Have you ever stopped to think about the invisible forces that make a summer day, well, a summer day? It turns out everything from the condensation on your cold drink to the breeze on your face is all run by some pretty amazing physics.
So, let's start with something we've all experienced. It's a hot day, you've got this perfectly chilled drink packed with ice, and yet you know it's not going to last. Sooner or later, you're left with a lukewarm glass of water. What's actually happening there?
Well, the answer isn't just because it's warm outside. The real reason is one of the most basic rules of the universe, a concept that controls pretty much everything. It's called thermal equilibrium.
Okay, so here's the deal. The universe is always trying to find balance. Heat energy just naturally flows from something hot to something cold, and it won't stop until they're both the exact same temperature. So the warmer air, your own hand on the glass, they're all dumping heat into your cold drink. And once everything's at the same temperature, the flow of heat just stops.
And you see this principle in action everywhere. It's exactly why a thermometer works. It has to reach equilibrium with your body to give you a reading. It's how your fridge works, pulling heat out of your food. And it's why ice is so great at cooling your drink. It's literally sucking up the heat from the liquid around it.
All right, let's take this a step further, because not everything heats up at the same speed. And this is something you've seen a million times, right in your own kitchen.
You know how it goes. You put a metal pan on the stove and it gets dangerously hot almost instantly. But the water you pour into it, that takes forever just to get warm, let alone boil. So why the huge difference in timing?
The secret is this thing called specific heat capacity. You can pretty much think of it as a material's stubbornness, its resistance to changing temperature. If something has a low specific heat capacity, it heats up and cools down super fast. If it's high, it takes a ton of energy to get it to change temperature.
And water? Water has an incredibly high specific heat capacity. Seriously, it's one of the highest out there for any common substance. This means it can absorb a massive amount of heat without its own temperature shooting up. That's exactly why we use it as a coolant in things like car engines. It can soak up all that engine heat and carry it away.
Now here's where it gets really cool. This property of water doesn't just impact our kitchens and our cars. It literally shapes the weather for the entire planet. It's the reason you feel a nice breeze at the beach.
See, land is a lot like that metal pan. It has a low specific heat capacity. The sun beats down, and the land's temperature just skyrockets. But the ocean, it's like that giant pot of water. It has a super high specific heat capacity. So even with the same amount of sun, it barely warms up at all.
And that huge temperature difference kicks off a chain reaction. First, the air over the hot land heats up, gets less dense, and starts to rise. Well, nature doesn't like a vacuum. So to fill that space, the cooler, denser air from over the ocean rushes in to take its place. And that movement of air? That's your refreshing sea breeze. All because water is stubborn about changing its temperature.
Okay, but what if you just keep pumping heat into something? Eventually, you do more than just raise its temperature. You actually start to change the substance itself. This gets us into the really cool physics of changing states, like when ice melts into water.
This is where we run into a concept called latent heat, which basically means hidden heat. Think about it. When ice is melting, it stays at a steady 0 degrees Celsius even though you're adding heat to it. So where is that energy going? It's not making the molecules move faster. Instead, that energy is being used to break them apart.
For a solid like ice to turn into a liquid, you have to pump in enough energy to just loosen up that rigid, crystalline structure. That's the latent heat of fusion. You're not totally breaking the bonds, but you're weakening them enough so the molecules can finally start to slide past one another. But to go from a liquid to a gas? Whoa, you need a lot more energy for that. The latent heat of vaporization is the energy it takes to completely break those bonds, setting the molecules free so they can escape and fly off as steam.
And you can see here, it takes way more energy to snap those bonds for boiling than it does to just weaken them for melting. This is why a pot of water can sit at 100 degrees for a long time while it boils. It's just soaking up a huge amount of that latent heat. It's also why a burn from steam is so much worse than one from boiling water. When that steam hits your skin, it releases all of that hidden energy at once.
All right, for our last stop, let's talk about the invisible world of gas, the air all around us. You know, whether it's the air in a bike pump or the fizz in a soda can, it's all controlled by a few really simple, really elegant rules.
These 3 laws are the key. They perfectly describe the relationship between the pressure, volume, and temperature of a gas. Basically, if you hold one of those 3 things steady, you can perfectly predict how the other 2 will interact.
Boyle's law is super intuitive. Just imagine squeezing a sealed plastic bottle.
You're decreasing the volume, right? That forces all the air molecules inside into a smaller space, so they start banging against the walls of the bottle way more often. And that's all pressure is, more collisions.
Charles' law is the reason hot air balloons fly. When you heat the air inside that giant balloon, the molecules get super energized and start zipping around like crazy. To keep the pressure the same as the air outside, they have to spread out, which makes the whole balloon expand. And because it's now less dense than the cooler air around it, up it goes.
And finally, Gay-Lussac's law is why you always see those warnings on aerosol cans. Do not leave in a hot car. The can has a fixed volume, so as the temperature inside climbs, those gas molecules start moving faster and faster, hitting the walls harder and more often, building up pressure until, well, you don't want to find out.
So you see, from the ice melting in your glass, to the sea breeze on your skin, to the very air you breathe, these simple, elegant laws of physics are working all around you, all the time. They turn an ordinary day into this amazing, invisible story of science. Makes you wonder, what else is being secretly run by these same rules?